Hey, feeling good, like I should. When in dark, walk around the neighborhood. Feeling blessed.
Alrighty, let's take a look at our homework for lesson 3.3.3. First, we've got our M&Ms for dividing decimal numbers. So just remember, when you are doing a division problem, the division problem, if you've got decimals involved, it can be kind of complicated. So we don't like using this what am I looking for? This division algorithm with any kind of decimal outside of it, because that means you're not going to line your decimal point in your answer up properly. So it's always a good idea to estimate. And remember my question, how many of these can you fit into there? How many 4s can you fit into 8? Your answer's got to be somewhere around 2, correct? It means that your answer is going to have a 2 in the ones place. But it's not always easy to figure out depending on what decimal numbers you're working through. So if we wrote this as a fraction, I guess it's written down here. Yeah, let's just show it down there. If you write it in fractional form, then you need to get rid of the decimal in the denominator. It is okay to have it in the numerator. It's not a problem. But if you feel more confident just completely getting rid of decimals, you could just whatever the greatest number of decimal places you have, multiply times the power of 10 with the same number of zeros. So in this case, because we do need to clear out these decimals in the denominator and you got 2 decimal places, you would need to multiply that times 100 so it becomes 407. And so this problem is now going to get written after you move the decimal 2 places to the right to 830 divided by 407. And if I ask the same question again, how many 400s can you fit into 800? You're going to say 2. And so we've got our decimal in the appropriate location because the 2 goes in the ones place, and that would be here. So working through the division process, the question that I always have students think about is, what would you multiply times 400 to give you this 800, right? And we're estimating, and you think it's a 2, so let's go ahead and do the multiplication. 2 times 7 is 14. We're going to carry the 1. 2 times 0 is 0 plus 1 gives you the 1. And then 2 times 4 gives you 8. And so when you bring this number down, you end up getting a 6 here because we had to borrow from that guy and make that a 10, and this becomes a 1. And then we put another 0 here. And then how many 400s can you fit into 160? And our answer would be 0. So we'd put it in as another 0. And how many of those go there? It's almost 4 of them. But it's going to end up being 3. And I'm like, okay, we can keep going on for a long, long time, but eventually we'd want to round it off. At some point you round it off, because look and see what the number is going to be when we actually do the division. 830 divided by 407. Yeah, that's a big, long repeating decimal. 039312, 039312. So you would have to go 7 digits into your decimal answer before you would start to see the repeating pattern. And nobody wants to do that. So generally in a problem like this, this is where you would just stop the division and round it to the nearest 10th or to the nearest 100th or to the nearest 1, I suppose. You could round it to any of them, okay? But let's just prove, right? Say our answer is 2.039, almost your 2.04. Let's prove that that works. Let's take the original problem, which was 8.3 divided by 4.07, and you will get the exact same answer. So this proves that rewriting this division problem after multiplying times a giant 1 so you get rid of your decimals, this is equivalent to the original, and that's a lot easier to work into our algorithm, so that's the one we want to work with. All right, Hilda was simplifying some numerical expressions and made each of the following sequences of calculations. Name the property. I'm so sorry. I never like doing these, and I know students don't like doing them, but it's good exercise. Name the property that justifies what she just did. So this one here, she's reversing the order of the 5 and the -4/3. So that's technically commutative property when you rearrange the order. And with the order of operations, you're supposed to go from left to right when all you're doing is multiplying. But it turns out if you wanted to do these guys first, you could group them with parentheses and it wouldn't change the answer. So associative property says when all you're doing is multiplying numbers together, it doesn't matter how they're grouped. Eventually, you're going to get to the same answer anyway. So multiplying 5 times 2/5 was a lot easier because that answer is 2. And now 2 times 4/3 is 8/3. So this becomes -8/3, which is -2 2/3. Here, same kind of an idea. If you want to rearrange the order of those two numbers, so you can add the 17 and the 13 first, then the 29 and the 1, now you can do this mentally, right? That's 30, that's 20, so your answer is going to be 50. What happened here? By after rearranging the order, we decided to add these guys together and then group those guys together. So instead of working from left to right, we grouped them differently. And even though, just like with multiplication, if you are only adding numbers together, you're allowed to rearrange the order, that's commutative property, or group them in whatever way seems logical to you, that's associative property. Once you get them down to nice, easy round numbers, then it's easy to add them mentally. And this is an illustration right here. I couldn't think of a better one for why we learn the properties. It's about making your jobs easier. Yes, you could have just gone from left to right and written these numbers down and added them all together. But by using a little bit of strategy and a little bit of creative thinking and understanding that these properties work, we're able to do it in our head, do it much, much faster. So that's the whole point of it. Once you understand how the properties work, they're meant to make your jobs easier. All right, simplify the following expression. So we got to do the parentheses first. So this becomes 4 times 2, which becomes 8, and 3 plus 8 ends up being 11. Here we must multiply first. I guarantee you, people are going to say 7 times 2 and have an answer of 14. But that is the wrong answer because you have to multiply before adding or subtracting. Multiplication has priority. Here the answer is 14 because we put parentheses around the 3 plus 4, giving the addition the highest priority over the multiplication. Same thing here. When we put parentheses around the 10 minus 8, that means you must do that before multiplying. So what was the lowest priority becomes the highest priority. So let's go ahead and see how we get 35 here. This is 40, and 3 plus 40 minus 8 becomes 43 minus 8, and 43 minus 8 is 35. Refer the diagram to the right, answer the questions. All right, so this has a value of -2 because you got 4 positives and 6 negatives, and 1, 2, 3, 4 zero pairs means really this is -2 once it's completely been simplified. So if that is a value of -2 and you can add positive and negative tiles, show the tiles you add to get this answer. Wait. Copy the diagram and add 2 tiles so that the result, oh, okay. So you have to put in 2 new tiles and there they are. And you don't want to change the value. You want to keep it the same. So the only way you're going to keep this having a value of -2 is to add a 0 pair. So by adding a 0 pair, it now becomes +5 plus 1, 2, 3, 4, 5, 6, -7, which is still equal to -2, just like this one, which was +4 times -6, gave you -2 for an answer. It says copy the diagram again, but this time remove 4 tiles so that the result is a value of +2. Well, if you take away 4 negatives and you've got these 2 0 pairs, that's going to leave you with 2 positives. So this is like saying -2 minus, you're taking away 4 tiles, right? And I took away 4 negative tiles. So -2 minus a -4 after using KFC becomes -2 plus a +4, which we know the answer is 2. And that's what our target was. So by taking away 4 negatives, we're left with eventually 2 positives after canceling out the 0 pairs that remain. Diamond problems. Copy and complete each diamond problem below. Remember, these 2 numbers get multiplied together and their answer's at the top. These 2 numbers get added and their answer goes on the bottom. So you have to use a little algebraic thinking. What do you multiply times -5 to give you -10 for an answer? Well, since your product is a negative, that means that one of the numbers had to be positive and the other one was negative. So this is going to have to be a +2. 2 times -5 is -10, and now that you know that's a 2, Then you add 2 to -5 to give you -3. Here, pretty straightforward. Multiply those two numbers together, add those two numbers together. Here is similar to problem A, where you have to think, what would I multiply times 3 1/5 to give me 16 for an answer? And to answer it, you're going to have to do the division. So you can estimate how many 3's can you fit into 16. It's a little bit more than 5, right? But that's not 3. It's 3 1/5. So it could be 5. It could be a little bit less than 5. Let's go ahead and show our work here. That's supposed to be a 16. Let me write this again. 16 over 1 divided by 15, 16 over 5. And now we'll multiply times the reciprocal of 5 over 16. And you notice you get those 16s canceling out. You could write it as 80 over 16 and then do the division, or cross cancel and see your answer is going to be 5 over 1, which is 5. So now 5 plus 3 1/5 is 8 1/5. And then this one is pretty much the same as A, just different numbers. You know that this number has to be a negative since that product is a positive. A negative times a negative will give you a positive 15. So what do you multiply times 3 to give you 15? It's 5. So if that's -3, that has to be -5. And then -3 plus -5 is -8. And that concludes our diamond problems. And now the last set of problems involving portions. Greta's trying to determine the portion of green candies in various bags of green and yellow candies. Use the information below to determine the portion of green candies in each bag. Okay, so 2/3 of the bag are yellow, which means the rest of them have to be green. So the rest of them must be 1/3. In this situation, 29% of the candies are yellow, which means the rest of them have to be green. Since the bag represents 100% of all the candies, 100 minus 29 is 71, so 71% of them, the rest of them, have to be green. And 4 out of every 9 candies are yellow, which means the remaining 5 out of every 9 have to be green. All right, so I think that ends our homework for this lesson, for this particular part. So let's go ahead and conclude and move on to our next activity, which is most likely getting ready for the chapter test. Take care. Bye.
Hey, feeling